All right, hello everyone. The purpose of this video is to go over some topics from lower division thermodynamics. And your book does this a lot, does most of this in chapter one. Chapter one is about the first law of thermodynamics and associated things. So this video is just a review for all of that because we're going to start pretty soon on the second law of thermodynamics in sort of a different way than we did as in lower division. Okay, so the main points here are like PV equals nRT, the first law of thermodynamics, which is conservation of energy, and then there's some particular processes that you should be familiar with, what those words mean and what they look like on a PV diagram. So those are the main topics for today. Okay, so to describe a system macroscopically, so there, first of all, there are some variables that only make sense sort of on average and with a large number of particles. And this is pressure, volume, and temperature. So these are macroscopic variables that describe the state of a system on average, pressure, volume, and temperature. And these are three variables that would be independent if there weren't for this thing called an equation of state. So an equation of state is an equation that relates these three macroscopic variables that takes the independent number of variables required to describe a system down to 2. So instead of there being 3 independent degrees of freedom, there's 2 because of this equation of state. And the most famous one is for an ideal gas. So this equation is only for an ideal gas. We can modify it and improve it a little bit with something called the van der Waals equation of state, which tries to take into account, intermolecular forces to modify the pressure term and volume of individual atoms for the volume term. But this is a good starting point. You're probably familiar with this equation. For SI units, you want to do pascals for the pressure, and atmospheric pressure is about 10 to the 5 pascals. 101,325 pascals equals 1 atmosphere, 1 atmospheric pressure. And a pascal is a Newton divided by square meters, right? That force over area. So SI unit of force divided by SI unit of area. And then the SI unit of volume is cubic meters. And then we have moles for the N. I'm going to put this, so R is just the real gas constant. I'm going to leave that blank for a second because that's just whatever it needs to be in order for all of these other units to work out. So it looks like that gas constant needs to have units of pressure times cubic meters. Now, by the way, all of these, so the PV and the nRT, those are both energies. So this is a number of joules, actually. So this gas constant is joules divided by mole Kelvin. So this gas constant is 8.31 joules per mole Kelvin. Yeah, so if you've taken a lot of chemistry courses, you might have seen that gas constant as being 0.0821. But that's a different unit. That's non-SI units. That's liter atmospheres divided by mole Kelvin. So if you have your volume in liters instead of cubic meters, so off by a factor of 1,000, and then your pressure in terms of atmospheres, so off by a factor of 10 to the 5, then this constant will be about 100 times less, with the numerical value will be 100 times less, but it'll be the same constant, just with instead of joules, it'll be liter atmospheres. A liter atmosphere is bigger than a joule by about a factor of 100. Okay. I probably can't go that slow for all of these slides, but introductory slide is the slowest. Okay, so let's see what a question might look like to test this. So this question doesn't immediately look like PV equals nRT. But we have which point corresponds to the highest temperature of the gas. So by rearranging the ideal gas law, we can write PV over nR is temperature. So the product of P times V on one of these PV diagrams is temperature. So if we were to just draw a hyperbola that goes through any one point, so this is a constant value of PV. P times V equals a constant for that hyperbola. every point on that hyperbola has the same temperature. And as you get farther out, so like this hyperbola right here have a higher value of P times V. Right? This is a bigger constant. PV equals a bigger constant, equals C2. So this first one was C1. This other one C2, and C2 is bigger than C1 here. So it looks like 2 is definitely bigger than 3 because you're going up and to the right. And anytime you either go up or you go to the right, you're jumping on a different isotherm and jumping up in temperature. So 2 is definitely a higher temperature than 3. 4 is definitely a higher temperature than 1. So we just have to compare 2 and 4, points 2 and 4. And we just need to look at the product of P times V. So if you look at this times this for point 2, looks like you have 200 times P1, whatever that is. And then there's some units associated with the volume. But just look at the 2 and the 100, it's 200. Versus if you look at 150 versus times 1.5, it looks like that's 150 plus 75 or 225. So 225 is bigger than 200. So it looks like that 0.4 has the biggest temperature, just because it has the highest value of P times V. Right? And we're assuming if we're plotting this, the number of moles is not changing. We're not changing the system here. And then, of course, the gas constant doesn't change as well. Okay, the first law of thermodynamics, energy is conserved. So you're used to this from mechanics class, that energy is conserved. Like mechanical energy is conserved. And then if energy is lost to friction, maybe you call that non-conservation energy. But really what's going on with that is that dissipative forces and energy lost due to friction is one of the main ones, probably the main one. So that energy is lost to heat. So this Q term right here is keeping track of that energy lost due to heat. So energy is conserved. It can change forms. And the mechanical energy term, most often we're talking about mechanical, a force over a distance, in which case that's work right here. And this is the work done on the system. So by the system, we normally, so a lot of times we're talking about a gas, like with the PV equals nRT, we're talking about a system of gas molecules, but not always, you could have a liquid or a solid as well. So you have some system that you're keeping track of how much heat is delivered to the system and how much work is done on the system. So in other words, if Q is positive, then the internal energy of the system goes up. Or if the work done on the system is positive, then the energy of the system goes up as well. So you should think of the system as just being some box, and energy can flow into that box, and it can flow in different ways. So you can compress the system, in which case you're doing positive work on the system, or you could just add energy via heat to the system. That will also increase the energy that's inside that box. So keep in mind that RW is work done on the system. The first law looks like this instead of Q minus W. So other books will call W the work done by the system, which is off by minus sign. So this integral of P dV is the work done by the system on its environment. And that's integral of P dV. So you need this extra minus sign for the W as we know it. So the work done on the system is minus integral of P dV. And for a PV diagram, we're going to see a lot of diagrams like this later on in this course. Integral of P dV is going to be area underneath the curve. So say a gas expands from state 1 to state 4 on this diagram. You could calculate the work done by the gas by finding that area right there. And that would be positive. If the gas is going from point 1 to point 4 along the path indicated, the work done by the gas would be positive, but the work done on the gas would be negative. You have to introduce that minus sign there. So work done on the gas is negative, which means energy is leaving the gas. If the gas is doing work on its environment, it's transferring energy to the environment and getting rid of that energy. So when a gas expands, it's losing energy in the form of work. And when it's compressed, energy is being given to the system. Okay, so let's try this. A gas undergoes a process in which 20 joules of heat is added to the gas. So in terms of our first law, that would be Q is positive and equal to positive 30 joules. We have our first law of thermodynamics formula. The change in the internal energy of the gas is Q plus W. So we know Q. Which of the following, 30 joules of heat is added to the gas, yet its temperature goes down. So this is actually a statement. So we didn't talk about this in the previous slide, but maybe as a hint for the next slide. So internal energy, or the thermal energy U, is a monotomically increasing function of temperature. So in other words, if temperature goes up, then U goes up, and vice versa. If T increases, then U increases. And if T decreases, then U decreases. So if one goes up, the other one necessarily goes up for an ideal gas. I should say for gas. So that helps us in this problem, because if we're told that the temperature goes down, then that necessarily means that U goes down, U decreases. And so if U decreases, delta U is negative. So a negative number equals a positive number, the 30 joules, plus W. So we can infer from the first law of thermodynamics here that the work done on the gas needs to be less than negative 30 joules. So from this, we can tell W is less than negative 30 joules. And remember, this is the work done on the gas. So the work done on the gas is definitely negative, which means the work done by the gas on the surroundings is positive. And the work done by the gas is integral of P dV is greater than 0, and therefore the gas expands. The gas definitely expands. All right. So yeah, for an ideal gas, it's monotonically increasing function of temperature. From the equipartition theorem, the thermal energy depends on the number of degrees of freedom. So this F right here is the degrees of freedom of the gas. Okay, so everything that we've talked about so far has been focusing on the macroscopic properties, temperature, pressure, and volume. But we can also describe what's going on microscopically. And for a gas, so a gas can definitely, no matter what the gas is comprised of, it can translate, it can move in 3 dimensions. So it has 3 degrees of freedom, always, no matter what the gas molecule is. And for each one of those degrees of freedom, it can store a certain amount of energy. And this is what the equipartition theorem is all about. For each degree of freedom, you can store this much energy, 1/2 kT. And this is per molecule. So if you want the total amount of energy, you have to multiply by the total number of molecules as well. I probably should have mentioned. Let me come back to this actually. So in this right here, the ideal gas law, this lowercase n is number of moles, and the capital N is number of particles. So they're both known as the ideal gas law. The NKT version, this has capital N being a very, very large number of molecules, in a macroscopic sample. So like 10 to the 23 molecules. And then K, which is Boltzmann's constant, is 1.38 times 10 to the minus 23 joules per Kelvin. So a really, really tiny number. And a lot of times we don't like dealing with a really, really big number times a really, really small number. So instead, we introduce something just called the number of moles. So we can take the number of particles and divide by Avogadro's number to get the number of moles of the sample. And then this turns n, capital N times K equal to lowercase n, number of moles, times this gas constant in term, per mole, molar gas constant. So, so the equipartition, the reason I bring it up is this equipartition theorem has to do with the energy per molecule. Okay, it's 1/2 kT per molecule per degree of freedom. So you have to multiply by both of those two things to get the total energy. Okay, so as I was saying before, every gas can translate no matter what the temperature is. And then this is sort of weird that you don't do anything. You can only move around. The gas molecules can only move around. We now are imagining a diatomic molecule where possibly you could rotate or vibrate and have energy stored that way. So because of quantum mechanics, quantum mechanics is kind of weird because you need, even just for something to rotate, you can't just give it a small amount of energy and have it rotate arbitrarily slowly. There are these jumps, like a diatomic molecule is not rotating, and there's some minimum energy that it needs in order to start rotating. It can only rotate in discrete values of energy. Like you can give it one packet, one quanta of energy, and then it'll start rotating. And then it needs a certain other amount to start rotating faster. It comes in these discrete steps. So because of this, you're not activating the rotational degrees of freedom until you get to around room temperature. It starts before that, but by the time you get to room temperature, then the molecules, but just by crashing into each other, they have enough energy. The temperature is kind of a measure of the average energy per molecule, average translational energy per molecule. And they have enough energy so that when they slam into each other, they can actually activate these rotational degrees of freedom. So this is to say that the number of degrees of freedom is 3 for low temperatures. And then if molecules are allowed to rotate, then the number is, you can either add 2 or 3 to this. So for diatomic molecules, or really linear molecules, it'll be +2. This is rotation about the two axes that are not the axis of the molecule. So this is for linear molecules. And then for nonlinear, it'll be 3. And then at higher temperatures, the molecules will start to vibrate. And then it really does depend on whether you have a diatomic versus polyatomic molecule. And really, the number of vibrational degrees of freedom can really grow with the number of atoms that comprise the molecule. But for a diatomic molecule, assuming it doesn't dissociate like hydrogen, like in this graph, then you can add 2 more vibrational degrees of freedom for a diatomic molecule. So for a diatomic molecule, 2 atoms connected together, you have F equals 3 for low temperatures. Diatomic. You have F equals 3 for low temperatures, F equals 5 for medium temperatures, and room temperature would be medium temperature. And then for really high temperatures, F equals 7. So this is related to how much energy is being stored for a given temperature. But it's also related to heat capacity. So this thing, heat capacity, is saying it's helping us relate how much heat you add, how much energy in the form of heat, and how much the temperature will go up of the system. Right, so right here. So one way that maybe we could write this is du equals Cv dt. So if I add a little amount of so the cause and effect here is really the other way around. If we add a little bit of energy, how much does the temperature go up? But written this way, it's like in order to increase the temperature a little amount, how much energy do I need in order to do that? And so from the equipartition theorem, we have U as a function of temperature. And by the way, this shows us our monotonically increasing function of temperature, right? The number of degrees of freedom is always positive. Boltzmann's constant is always positive. So if we take a derivative with respect to T, we see this heat capacity, which depends on the number of degree of freedom. This is the extensive heat capacity, meaning it scales with how big the system is. So it'll depend on how many moles of particles you have. The intensive molar heat capacity, or per mole, it's just dependent on the number of degrees of freedom times this real gas constant. So what's being plotted right here is just the molar heat capacity, and showing how it can depend on temperature because of quantum mechanics and because you need higher temperatures to excite those degrees of freedom. Okay, suppose I have 10 joules of energy that I want to give in the form of heat to a sample of air in a rigid container. So if you ever see rigid container, that automatically means V equals 0. Or sorry, delta V equals constant. And so if V is constant, then there's no work being done. W equals 0. We're not mechanically compressing, or the system's not expanding. And so what this means from the first law is delta U equals Q. And from calorimetry, we know Q, or not only calorimetry, but here, Q is N. So this is a little tricky because, you kind of have to infer from context whether the heat capacity is extensive or intensive. See how these two are both labeled as CV, but they're not the same. And some books will use them kind of interchangeably. And you have to look at the other side of the equation to see, oh, does it depend on how big the system is? Whether it's extensive or intensive. So I'm going to write this one this way, CV delta T. So because there's no N hanging around on this side of the equation, we can see that this CV is the extensive heat capacity. It will depend on how big our sample is, how many moles of gas we have. Okay, I have 10 joules of energy that I want to give in the form of heat. So this Q right here is going to be 10 joules. In order to get the largest temperature change. So the largest delta T comes from the smallest heat capacity, smallest CV, for a given amount of energy and given amount of heat in this case, because there's no work being done. So the smallest heat capacity will be with the lowest number of degrees of freedom, and this will happen at the lower temperatures, because here the molecules can only translate rather than rotate or vibrate. Okay, what fraction of the thermal energy of room temperature gas is rotational? So the total number of degrees of freedom here is 5. Right? It's 3 translational and 2 rotational. So this is translational degrees of freedom and rotational degrees of freedom. Room temperature gas is it's like 70, well, close to 80% nitrogen and 20% oxygen. There's other stuff. It's like 1% argon, maybe some water vapor, stuff like that. But for the most part, it's this. And these are diatomic molecules. So the rotational degrees of freedom are 2 degrees of freedom, not 3. Remember, it's 3 for polyatomic molecules, but not here. So if we assume that at room temperature, all of the rotational modes are excited, remember that this graph said that there was a ramp up region, right? But suppose we're not in that region. We're in this region where all of the molecules are rotating. Then the number of degrees of freedom for all of the gas molecules is 5. So it looks like 60% of the energy is translational and 40% is rotational. Okay, because remember, for each degree of freedom, the energy is split evenly over those degrees of freedom. So over these 5 degrees of freedom, that 3/5 of the energy is translational, 2/5 is rotational. So what fraction is rotational? 40%. So this has to do with knowing the total, the degrees of freedom, and how they're split among the various degrees of freedom. Okay, 4 processes. So on a pressure versus volume diagram, we have isobaric constant pressure process. So suppose a gas starts off here and it moves horizontally. That would be constant pressure. So the pressure is the same as the starting value right here. So these are called isobars, isobaric process. And we like to have some indication of where the start and the finish is. So a lot of times an arrow is drawn in here. So by the way, the drawing a line on here is sort of a non-trivial statement that, what we're saying here is that the gas was slowly taken to say this final value right here. And it had a well-defined volume and pressure along the way. So when we're drawing things on the PV diagram, we're drawing quasi-static processes where there's enough time. Quasi-static means almost still, meaning that the process is done so slowly that the system is coming to equilibrium for each stage in the middle of all this. Generally, if you have a gas and you just very, very quickly suppose for some reason like a balloon explodes, it's a very non-equilibrium situation with like the gas molecules, which are now suddenly able to fill the whole room. But if they're still contained right here, it's like, well, what's the volume of the gas? Like say it's kind of slowly creeping out, but there's no well-defined volume. Some of them are zipping out in various directions. So this is not that, right? This is a well-defined volume along the way. Okay, isochoric is constant volume. So we could go along this way. So isochoric process, constant volume, and in order to increase or decrease the pressure, you would have to heat up. That's the only way for energy to change because there's no work being done in an isochoric. Then the other two are, okay, so if I take the first dot right here and I drew that hyperbola like we were talking about before, where PV equals constant, this is constant temperature. This is isothermal. So if we go along that path, then that's an isothermal process, constant temperature, which also means delta U equals 0. So in the case of a gas expanding, so I drew this arrow right here to indicate that the gas was expanding, the volume was increasing. The gas is doing work on the surroundings. The positive work is done by the gas. Negative work is done on the gas. So by negative work done on the gas, if W is negative, that means energy is actually leaving the system rather than going into the system. So energy is leaving the gas. How is delta U equals 0? Because this is also saying that there's no overall change in energy. Well, if the work is negative, that means the heat is positive. So you have to keep replenishing the energy in the form of heat to this gas so you're heating up the gas, and for every 1 joule that you give it, it's doing 1 joule of work on its environment to expand. And the overall effect is that there's no changing in energy of the gas, which is 1-to-1 with there not being no change in the temperature of the gas. But what if the gas is expanding and you're not giving it any energy? This is called an adiabatic process. So in this case, the internal energy will go down, right? If the gas is expanding and you're not replenishing that energy, then the energy is going to go down and the temperature will drop. So that's what this looks like. These are adiabatic processes, and they're steeper on a PV diagram than an isothermal process because the internal energy is going down as the gas is expanding. If you compress a gas, and these tend to be quick processes because the heat work is basically instantaneous. The energy transfer is instantaneous, but for heat, it takes some time in order for you to transfer energy via heat. So adiabatic processes are more similar to, these are basically fast. Remember that this is kind of a contradiction because we're saying that all of these processes are done slow enough that there's an equilibrium temperature being reached. So this is fast compared to the other three processes. Fast enough that no heat is being exchanged, but still slow enough, or at least we're modeling this as being quasi-static. Okay. So maybe this video's gone long enough. Maybe I'll post another video to go over the three examples here. Well, no, I can do this pretty fast. This will just take 10 minutes. Okay, when I add heat to a diatomic gas that's rotating but not vibrating. So as soon as we read this, we know that the total number of degrees of freedom is 5. Right? Diatomic, rotating but not vibrating. When I add the heat at constant volume, the temperature increases by 10 Kelvin. How much would the temperature increase if I gave it 10 kilojoules of heat at constant pressure? So this is, so here's a formula that we haven't quite gone over yet. But the heat capacity at constant volume is F over 2R. And there's another relationship for ideal gases that Cp is Cv plus R. So where does this come from? This is basically the statement that, say let's look at an isochoric process versus an isobaric process, and the gas is being heated up in both times. So not just heated up, but the temperature is going up in both those cases. So up for the isochoric and to the right for the isobaric. If you want the same temperature change, so say you're jumping up to this hyperbola, you need to give more energy for the isobaric, more energy in the form of heat to the isobaric process, because the gas is getting rid of some of that energy as it's expanding. So you have to replenish that and give it more than that in order to increase the temperature. Versus the isochoric process, everything that you give it is going to go towards increasing the temperature of the gas, and none of it's wasted to the gas expanding. So for this example, the temperature is not going to increase as much because I'm giving it the same amount of energy, but it's at constant pressure, isobaric. We're going to go to the right on the PV diagram. The gas is expanding, and it's going to it's going to waste some of that heat by expanding. It's got to do work on its environment in order to expand. So the answer is going to be less than 10 K. But because of this, so going to the right on the PV diagram is a nice rectangle, and because of that, you can show that there's this nice relationship between when you add something at constant pressure, when you add heat at constant, when you add energy in the form of heat at constant pressure versus at constant volume, there's a simple relationship between those heat capacities, and this is what it is. So there's sort of the first setup. So for both of these, we're going to use Q. So we want to relate the heat that we're adding to the gas versus, and let's not we're not told anything about the number of gas molecules or anything, so I'm going to use the extensive version of this, Q equals CV delta T. So for the first one, we have 10 kilojoules was 5/2 R times delta T. We'll call it delta T naught for the original setup. Okay, and this was the 10 Kelvin. 10 kilojoules equals 5/2 R times 10. And actually, we would need the number of moles here, right? We can't just, because yeah, otherwise this would be, the statement would not make sense. So 10 kilojoules is N 5/2 R times 10K. So we could actually, we could solve for the number of moles of gas that we have as well. Okay, and then what we want to see is if we took that same amount of heat and we instead added it at constant pressure, in which case this would be 7/2 R for the, this would be, so this Q equals NC CV delta T, this is for isochoric. For isobaric, you have to use a Q equals NCP delta T for isobaric. Right, the CP. So in general, there's not a nice relationship between Q and delta T. These are sort of the only two, these are two of the main exceptions. So for example, for adiabatic, Q equals 0. So you can't say that Q is dependent on delta T in a certain way like this. Because delta T is non-zero for adiabatic, but Q is 0. So for some special processes, you can write a formula for how Q depends on delta T, but these are special cases. Okay, so times delta T1. So it looks like delta T1, if we just combine these two equations, you get delta T1 is, it's going to be less by a factor of 5/7. It'll be 5/7 delta T0. And originally this was 10 Kelvin. So this is going to be 70, was it? 71, 7.1 Kelvin. Okay, a gas expands according to the equation PV squared equals constant. Give the sign of W, Q, and delta T. Okay. So remember that so first of all, gas expands, which means that W is negative, right? The work done by the gas is positive, the work done on the gas is negative. Right? So we know the sign of W right away. Now, if PV is constant, it looks like this hyperbola, right? This is PV equals constant, but that's not what we have in this problem. Right now we have P times V squared equals a constant. So let's see how we would analyze that. Okay, I think, so basically we want to see, I'm going to play with differentials to find the answer, but let me try and motivate why I'm doing what I'm doing. So right here, there's a certain value, for the hyperbola, there's a certain value of dp dv. So first of all, dp dv is definitely negative here for hyperbola. And you can show that from the ideal gas law. So if pressure is proportional to if P is proportional to 1 over V, then you can show, dp dv is negative. Just because when you take a derivative of V to the -1, you get a negative right there. So basically, we want to see, for this case, right here, this PV squared is constant, is this going to be steeper? In which case, as the gas expands, we're going to jump down to a lower isotherm. Or is it going to be shallower like this, in which case the temperature would actually go up as the gas expands? So we need to find dp dv and relate it to the dp dv for isotherm. Right. This one is probably better done using some algebra. So basically, I'm going to find dp dt for both those two and see which is steeper, and then reason out the answer that way. But that's probably better done just in the notes. That's maybe too much algebra for the video. I don't want the video to get too long. So I'd rather do this one and leave that one for work that we'll post on the website. Okay, so what about this one? Sketch a possible process on a PV diagram for this bar chart. And so we have P dV. Okay, so one thing that I see right away is that there's this and there's this. This is taken from a book where they use E thermal instead of U, but this is internal energy. So one thing to see right away is delta U is positive, which means that delta T is positive. So we're jumping to a higher isotherm. So if our initial point is on here, our final point is going to be on a higher isotherm. So initial versus final isotherm. And then the work is negative also. So W on is negative, which means the work done by the gas is positive. Right? Which means that the gas expands. Gas expands. So we need to go to a higher final volume. B final is bigger than B initial. So we need to jump from a point on this isotherm onto this isotherm and have the gas expand. Okay, so and then the Q is just whatever, the Q will depend on which path we draw, because I could draw it from here straight over to here in an isobaric process, or I could just draw, a straight line path up like this. And this isn't one of those processes at all that we talked about. So Q will depend on exactly which path we have. Q is a path dependent thing, just like or quantity, just like the work. But looks like this satisfies all of those demands. Right? Delta U is positive, the temperature goes up, and the gas expands. So this looks good. Okay.